Okay.
Yeah.
Jeff is really nicely written this out.
Yeah, I want to make sure I got it right.
Okay, so for category C, we've got three sheets. So we've an instance of C op. So here, category C is our indexing category, and we take the opposite of it. And so it bears noting we're not dealing with a sort of traditional C set. We're dealing with an indexing category whose opposite we want to deal with, right? So we're dealing with one of these, for example, for the bouquet category, where this is our indexing category, and we're going to then take its op like this, and we're going to map it into sets. So there'll be a set of L's, a set of V's, and a map between L and V. Okay, so that's right. Yeah. Yeah, so we're going to have this instance of this. Okay, great. And now, for all C and C, that's right. For all the objects, you're going to have a representative. You're going to have a representative. Special form. And a key thing here is this. Right now, this says nat. The key thing is this is taking place in a functor, category. So it's taking place in the category of appreciations. So this is a hum. And this nat, what did you mean by nat?
Natural transformation.
Oh,
sorry, natural isomorphism.
Well, this is actually going to be the category of where objects in this category are species. Objects are functors from C op to set. I don't know. That's where I can see this. Concern and not be able to see it because there's this kind of light on the board. Maybe I can. Okay, I got to be careful here. There's a strict rule back there about where the thermos can live and where the computer. Okay. Would one of you mind getting the lights because it's kind of reflecting the lights off of it? Okay. Sorry. So we're in this category, and can you still
check the zoom?
Oh, check the zoom. Yeah, it looks better now to my untrained eye because the glare is not as bad. So this is called the functor category, and I don't want to thanks a ton, but that's great. That works well. Yeah. This is a functor category. So each object is one of these functors, one of these presheets from C op to set. Each of them is an instance. Maybe it's a diagram with bouquets, right? Something like that, right? Like this, something like that. So each of these dots is one of these. Or each of the, if C op is the graph schema, then each of these dots would be a graph. Are we okay with that? Now, there are morphisms in these categories that are natural transformations. They're structure-preserving mappings between these things. So they might map one bouquet diagram to another where maybe this one maps to you need at least one loop. It's a homomorphism between these. They're structure-preserving mappings between these, right? This maybe maps onto that. I'm drawing what the natural transformation does. This maps onto that. And like this dot goes to that one, and maybe these bouquets here go down to different ones. This one goes to that one too. This one goes to that one. There's several that got squished down. Maybe each of these goes to those three or whatever. This one goes to that. Okay. So this is a natural transformation from this functor to this functor with the same C. Like everything here is with the same indexing category C. Are we okay with that?
Mm.
This is a natural transformation. This is one of these kind of mappings, or maybe this embeds in another one. All these go and they're nicely embedded in another one, right? Right? That's what these things are. Now, some of these, though, are dots not like the others. Some of these are special dots. Some of these are beautiful dots. They are like at the heart of this. They're like the basic building block dots. And these are going to be these hom functions. These represent. And what we're saying here, what Jeff is saying here, is quite right, exactly right. That there's one of these for each C, but this is actually, I don't know if I'd call this in a category of natural transformations. I think I'd call it in the category, the functor category C set, where maybe it is called NAT. I can't remember what NAT remembers, but like the category of natural transformation, one thing in category theory you'll find is that when people say the category of X, sometimes they're referring to the morphisms and sometimes they're referring to the objects. And it's kind of confusing to me. I think NAT could be object morphisms with natural transformations being the objects and something else being the morphisms, but I'm not sure of that. So I want to write it specifically. It's also not generic natural transformations. It's natural transformations between C opposites. So there's one of these guys for C1, this is another one, for C2, maybe this is another one for some other object in the category C, by extension C op, I'll write it home and C. I don't even C3 or whatever. By the way, instead of writing it hom and C, maybe that's kind of old school. Maybe I'll write it C1. Right? Like it's the hom functor. It's a functor. All these are functors. C op to C. That's what this dash is.
Yeah.
Fill in the object and you get a set. Fill in the morphism. Fill in the morphism and C, and you get a mapping of function between sets. So there's these, and these are connected together. Maybe this one, like the hom for edge, maybe it maps down to the hom for vertex or whatever. And one of set of natural transformations, isomorphic. Yes. The set of natural transformations. That's right. Set of natural transformations from one of these to F for pre-sheaf F. Yeah. So that's one of these diagrams, one of these like bouquet diagrams, and the set of these from a given representable, like maybe it's the representable for loop. Representable for loop. The set of those, set of mappings, yeah. The set of mappings here is in one-to-one correspondence with, basically are given by. Another name for them is just these, the set of these. So for every one that's there, you can find it. For every one you find, it's one of these. Does that? That's the represent. That's the representable for C. That's right. That's right. And there's one of those, yes, you said for every. Yeah. Wow. So you can find them. And these are these natural building blocks. And any search is going to be composed of these things. of these blocks. And so if you can reason about where those blocks are, and sometimes reason there's none of them, you may be able to speed up many searches and have many effective searches. But this is the picture. And the amazing thing, and Eugenia Cheng does a masterful job in her book laying this out. This is an extremely deep result. It took me 5 years, 5.5, 6 years probably, to really start to better fully appreciate this. But it's a very useful result too. But it speaks about the fact that things are connected at two very different levels here. This is about kind of the set map to that F that our functor maps a given object to, like how many loops are there in here. This is about finding kind of one functor, like the number of natural transformations from this functor to this guy, number of homomorphisms in. You might think those are at two different levels. This is kind of about pre-sheaves, morphisms between them. This is about data associated with the, our pre-sheaf. But actually, there's this deep connection. The structure here translates to structure here. And that's, or vice versa. I'd have to think the better way to put it. But like, it does make sense that like you can find one of these, for every one that exists, you can find it. And this is kind of finding it. It's like doing a hom search of like finding, where can I find these in here systematically? Where are the mappings of this in? Yeah, it kind of makes sense that if this is the way of looking for a C, this representable is kind of the way of the building block for the C, the minimum building block for a C, minimum building block for a C, right? You can't have an edge without having vertices. Like, it doesn't make sense to have some like disconnected edge, disembodied, no vertices. You can't have, you shouldn't be able to have a person without a home, right? And so it kind of makes sense that if you search for the minimum things need to have a C, without which it won't be a C set, that gives you the number of them. That's kind of, I don't know if this helps at all here.
It's helping a bit, yeah. There's bound to be an aha moment at some point in the future for me where it just kind of clicks.
Yeah. It took me many years, but talking about it helps. I know, and one thing that's very hard is going between these levels of abstraction.
Right, because we're talking about a category and a functor and an element of the category.
That's right.
And the size of
that's right.
the homomorphisms.
That's right.
So many things that
that's right. That's right. But again, this is like seen as a pinnacle of like if you can really understand this, you're doing exceptionally, you're really I think quite far along. But yeah, I think of it as kind of, we're finding the minimum things we could do to specify C in F, and that gives us the number of those things here. It's kind of the way I think about it. And as Matthew said earlier, and indeed, that was the point I'm trying to make, is like if we want to find one diagram and another, one pattern. So Jeff, we use these things in nature-based modeling to search for patterns, like make this rule happen when this pattern is matched. So like you have a susceptible and effective next to each other, or susceptible in fact to share the same home. That might be a pattern. And you want to find that in your state of the model. You're like looking for people who are in the same home as someone else so they're infective, someone else is susceptible in that home, and we're going to make something happen like we'll infect the susceptible person. And so we want to find a pattern within this maybe really big state of the model, tens of thousands of things or whatever. There, it's very valuable to ask to know quickly, like, do I not have to search because it's an impossible search, like because there won't be any of them, or to reason about like this bigger whole query. If I could know about how different parts of it can get matched up, maybe I could do the whole thing much quicker than just brutally looking to find these instances of patterns here that match it.
For example, if we have a hypothesis about something, we have a database and we have a hypothesis about the relationship between the object in this data set. Yeah?
Right.
If we have a complex hypothesis, we can break down with the simplest hypothesis and find each of them.
That's right.
In the model.
Yes. Yeah, exactly. That's along the lines of what I'm thinking too. Now, Chris Brown has done an amazing amount of work with incremental search for this. Doing these searches incrementally as well, which is important. Yes. Yeah. 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 From functor to functor. That's right.
That's one of the things I was
That's
trying
right.
to grasp.
You're finding one functor. Again, you could think of it, if you want, you could kind of zoom up and say this is just a bouquet diagram. You're finding it in another bouquet diagram. But it is a functor to functor. And that's therefore what you're considering is in this category, the number of morphisms from this to this. The functors here are just dots. They're for all functors for the same C. They're just dots. The morphisms are the ways of matching the number of matches of this in this. Think of that, sort of the number of places you can find this in here. But it's a functor. It is a functor. Now, it's nice to not be able to say to not have to think all the way through what a natural transformation is, but really that is behind it. It's finding it in a consistent way in here that's natural. But really it's sort of finding it in this. And it's morphisms, counts of morphisms of these, because each morphism is a homomorphism. Each morphism is like a place to find it in.
In the slide, theoretically, it's using the similar or equal to symbol, but in Haskell, it's congruent to. Do you know why?
Yeah,
Isomorphism, I think is what that.
is the isomorphism. Yeah, this is a one-to-one.
I had to look into it because the
one-to-one.
Copilot actually writes the text of the LaTeX, which is
Right.
class CONG. And so I looked up what does CONG.
Yeah, CONG is
Congruent.
congruent.
Yeah, I mean, sometimes I'm a little bit confused because sometimes it's written like this, I think. But
Yeah, I remember.
I think it's just saying there's a one-to-one, there's a bijection between the sets. Yeah.
I'm just trying to find I remember I saw this symbol in this book when
In the
section of natural transformation.
Yeah, that's right. That's right. That's right. That's right. So let me check my schedule and figure out how I think I've